Okay, welcome everyone. Good afternoon. It's a pleasure, and I mean it, to introduce our speaker today. He is Dr. Miguel Hoyuelos. He comes from the Institute of Physics from the University of Plata in Argentina. He got his master's degree in physics in the Institute Balseiro in Bariloche, Argentina, and his PhD in physics in 1994 in the University of Plata, where he is now. And we had the pleasure of having him with us as a postdoc in what at that time was in Medea in 1997, 1998. At that time he was working with Vera and me and others in nonlinear optics, in pattern formation, in nonlinear optics, in two European projects that we had at that time. And he was the first one coming from Mar del Plata to Mallorca, and after that we've had all of the postdocs and students coming from there. You might remember Fabi Cruz and Adrian Jacobo. So we have a strong link with them. Federico Vázquez also, yeah. So we have a strong link, and Miguel is here to reinforce the link and to find new collaborations. All his work has been in the field of statistical mechanics, started with reaction processes of annihilation, reaction diffusion, and other types of nonlinear physics. But I have to say that beyond that, he is a person with a broad range of interests. He has some books outside the realm of physics. One, for those of you that understand Spanish, I recommend, which is El Horóscopo Argentino. And he has been spending some time in the last years looking into the life of all these physicists active in the field of statistical physics that had a turbulent life that ended in bad ways, like Ehrenfest, Boltzmann, and the like. And he will give a very general talk here on Monday at 12 in Spanish on the contributions mixed with their personal life of all these scientists that went on this freaky sort of behavior. I hope that none of us finishes as some of them, but today it's a scientific talk that we're going to give on the generic framework for reaction diffusion systems. I understand it goes into the direction of general formulation of thermodynamics, and they're here to listen.
Okay.
And then to ask.
Okay, thank you very much for the presentation. I'm very happy to be here. I have very good memories of the time spent here in Mallorca, and I'm very happy to see many good friends. So, well, I have to speak about physics now. It's generic framework for reaction diffusion systems. This is the outline of my talk. I will give an introduction to this generic theory. It is a theory for non-equilibrium thermodynamic systems that is proposed as a general framework. Some applications to reaction systems and to the Fokker-Planck equation. Some examples, and at the end the conclusions. So perhaps one of the most difficult tasks of this theory was to find a combination of words to make this acronym. This is general equation for the non-equilibrium reversible irreversible coupling. Well, this general equation is proposed as a unified point of view for different non-equilibrium phenomena, but it has a limitation. It is only for isolated systems. I will give you just a generalization for a system that is coupled with a reservoir, and we have to consider the combination of the system and reservoir as a total system. And the theory is applied only to the combination. I mean, it is only for systems for which the energy is conserved and the entropy always increases. The good news are that it holds beyond local thermal equilibrium and also beyond linear non-equilibrium. What does this mean? The theory for non-equilibrium thermodynamic systems that was developed during the 20th century is what is called the classical irreversible theory or classical irreversible thermodynamics. Uses these two approximations, local thermal equilibrium and linear non-equilibrium or linear relations. Well, what is local thermal equilibrium? You have, you know from thermodynamics that the temperature is only defined for equilibrium systems. But you, in a non-equilibrium system, for example, a fluid, you can divide it in very small cells, small enough to be point-like, but at the same time, they must be large enough to contain many particles. So each small cell can be considered as a thermodynamic system with a temperature, and each of these small cells have a well-defined temperature. So you define a temperature field in the system. Not one temperature for the non-equilibrium system, but the temperature field. This is local thermal equilibrium. So each cell is in equilibrium, but the whole system is not in equilibrium. You have a process of heat converting from high temperature to low temperature. And the other approximation is this one. Linear. It is called linear non-equilibrium. You have to have a closed set of equations. You have to introduce other equations that are called generalized Ohm relations, in which you have linear relations between currents and forces, thermodynamic currents and thermodynamic forces. For example, a thermodynamic force is a gradient of temperature. And this force drives a current of heat. You propose, the most general approach is to propose a linear relation between the current of heat and the force, the gradient of, this is the Fourier law of heat conduction. And there are others, for example, between the flux of momentum and the gradients of velocity, you introduce the viscosity. In the case of the flux of heat, you introduce the thermal conductivity, different transport coefficients. But there are systems, this is very useful. This theory, this classical irreversible thermodynamics, was very useful and also today, and mainly in the second half of the 20th century, to describe a lot of systems. But it has this limitation. There are situations in which these approximations do not hold, especially when you have processes with very small space scales and very fast time scales. So in this moment there are different theories that are competing. There is not a well-established theory for non-equilibrium thermodynamic systems. One of the theories is this generic. Perhaps you also already heard about the extended irreversible thermodynamics that was developed by some people here from Spain, like David Shaw and Casas Vázquez. The main problem that you have when you don't have this linear relation between the forces and currents is that you need more equations or more variables to describe the system. In classical irreversible thermodynamics, you have for hydrodynamic equations, also called thermo-hydrodynamic equations, well, doesn't matter. You have this set of variables to describe the system. This I will call X, capital X, the set of variables that the of state variables. And for hydrodynamics, you have the density of mass. This M represents the density of momentum, and this epsilon is the energy density. In some cases, instead of the energy, you can use the temperature or also the entropy. But originally, this is composed by this that represent conserved quantities. But this is not enough beyond linear non-equilibrium, because you don't have the linear relations between forces and currents. The proposal of the extended irreversible thermodynamics was to add fluxes. Now, to consider these fluxes as independent variables. So you have more variables, more state variables. In the generic framework is somewhat more flexible, so it is a guide for the selection of additional variables, but does not give you a specific rule to adopt them. You have to see in each case what are the appropriate variables in order to satisfy some conditions that are given by the framework of this theory that we will see now. The first step is to separate. You have a set of variables. These are the state variables that describe an isolated system. And you have a set of differential equations that describe the evolution of these variables. The first step is to separate the reversible from the irreversible parts of these equations. The reversible part is the one that is associated with the gradients of energy, or the derivatives. When I say gradient, I refer to the gradient in the space of the state variables, the derivatives with respect to these state variables of the energy. This is the mechanistic part of the dynamics, the one that can be associated with the Hamiltonian, like in classical mechanics. This time evolution is associated with the Poisson bracket, and it has the derivatives of the Hamiltonian or of the energy. This is what I refer to when I speak of the gradients of energy. And the irreversible part is associated with the gradients of entropy. The gradient of entropy is what is called also the generalized thermodynamic forces. And these are connected with forces, thermodynamic forces that appear spontaneously in the system when the system is out of equilibrium and drives the system again to equilibrium. Of course, if you are in equilibrium, the entropy is maximum and all these forces disappear. The gradients are all zero. So now, this is the form that the equation should have. This is the reversible part proportional to the gradients of the energy, the derivatives of the energy with respect to the state variables. And this is a matrix that is called the Poisson matrix, and here appears the friction matrix, that is multiplies the derivatives of the entropy. These are partial derivatives if these are functions of x, but the variables x could be first, so in that case these are functional derivatives. There are some conditions. This Poisson matrix must be antisymmetric, and the friction matrix is symmetric and positive semi-definite. And there are two more conditions that are the degeneracy requirements. I wrote here again the equation, the general form of the evolution equation of the system, and this Poisson matrix times the derivatives of the entropy should be equal to 0, and the derivatives of the energy times the friction matrix should be 0. It can be multiplied from the left or from the right, because this matrix is antisymmetric and this one is symmetric, so it is the same. You multiply on one side or the other. With these conditions and with the definition of the condition on each of these matrices, the conservation of energy and increase of entropy follows immediately, because the derivative of the energy with respect to time is all this. I mean, the derivative of the energy with respect to x and the derivative of x with respect to time, and then the chain rule. And here this disappears because of this condition, and you have only this product. Since L is antisymmetric, this is equal to 0. So energy is conserved. And in the other case, the derivative of the entropy with respect to time, this is total energy at total entropy. No? because of this condition, this disappears here, and you have only this, that since M is a positive semi-definite, it's always positive or zero. So you have always an increase in entropy. What's the motivation to do all this? Because in principle you already have the equation, the differential equation to describe the system, and it seems at the first sight that you only present the same equation, it's just in another shape or in another form, in another framework, but you don't have new equations with this. The motivation is the following. Oettinger in his book about this book about this generic framework of 2005, written by Oettinger, and he makes an analogy with equilibrium thermodynamics. That is the following. In equilibrium thermodynamics, you can have state equations that gives you an understanding of a particular system. You can have, for example, a relation between pressure, temperature, volume, internal energy, that gives you a complete description of a given system. But only when you see the hidden structure behind this equation, that the relation of this equation with the free energy, you understand the thermodynamics. Because this set of equations are part of a larger class of equations that satisfy this structure, the thermodynamics structure. So, only with the state equation you understand the particular system. When you understand the structure, you understand more the thermodynamics. And this is something similar happens with or this is at least the intention of the theory. Something similar with the generic theory. You have at the first step a set of differential equations that gives you an understanding of a particular system. But when you put this differential equation inside the framework with the given structure, you have a deeper understanding. I mean, you can a deeper understanding of non-equilibrium thermodynamics and also of the role of the entropy and the energy in the system. I don't know, it's something difficult to explain this, because when you see this, it's like the search of universality, you know? When you see that all systems obey the definite structure, you feel that you are understanding more. This is, I think, the sensation. Although you are not introducing new equations. Well, there are the applications, the main applications of this theory were these two fields, the complex fluids and relativistic hydrodynamics. In complex fluids in which, or rheology, in which you have deformation and flow. In these cases, you have to consider also the elasticity of the system. Well, there's several examples where of the application of the theory, polymer mats, liquid crystal, fiber suspension, cold emulsion. These are all examples where the linear relation between fluxes and currents do not hold. You don't have, especially for the momentum flux. You have to consider other. It's not possible to write the momentum flux proportional to the gradients of position. You have to consider also elasticity. Well, also in relativistic hydrodynamics, especially in cosmology problems, dissipation in the early universe because of the extrinsic conditions in this. So you cannot use local thermal equilibrium.
Well, just one more question. At the beginning you said that in this formula the energy is conserved.
Energy is conserved. Yes.
So how do you tackle dissipation in a system that conserves energy?
Dissipation in the universe, I don't know, but I think that they consider the universe as a system, complete system, and you don't have nothing outside. Yes, this cosmology theory always the system is the universe. I suppose it is especially between different parts of the system. Well, now some examples. I will give you, just to have a flavor of this theory, 2 examples for more simple situations than the I previously mentioned. One of these is a general reaction system. This is a way to write the rate equations for an arbitrary reaction where you have m reacting species with concentration, this is the vector of concentration, and 1 to n, and you have r possible reactions. These j are the reaction rates for reaction number j. These are the reaction constants for forward and backward reactions. And this is alpha j and beta j are also vectors that are the stoichiometric coefficients for the backward and for forward and backward reactions. And in this notation, this vector to the power of this other one is the product of each component of the concentration to each one of the components of this vector, the stoichiometric coefficients. So in this way, you can write, in general, this equation for the concentrations, and this R that depends on n is the product of this matrix. That is the matrix of the difference of stoichiometric coefficients, then backward and forward coefficients, times the vector of the reactions, reaction rates. In equilibrium, this is restricted only to situations, to isolated systems. So for a large enough time, you reach the concentration values that correspond to equilibrium. In this case, we assume that in equilibrium the tile balance holds. It means that all the reaction currents are 0. So the forward reaction is compensated by the backward reaction. And in this case, for this equilibrium solution, then you can write the reaction rates in this different way. Well, it doesn't matter very much. It's just to show you that there is a general way to write a reaction system, but it is not any reaction system. I mean, it does not represent, for example, the reaction system that we are interested in when you look for a pattern formation, because in that case, it is not isolated. You fix one concentration in a given value from outside, and with this external forces you don't reach this value of equilibrium, and the currents are kept different from zero. But in this situation, when all the currents are equal to zero in equilibrium, we can put this into a generic framework. The evolution is only irreversible. You don't have the reversible part, so the Poisson matrix is equal to 0, and this is the form, general form that we are reaching. We are looking for a matrix. This is the dissipation matrix or the friction matrix, and the derivatives of the entropy should be equal to R. Well, this is solved when the friction matrix is equal to this R. This is a dyadic tensor. Now this is a matrix composed by a vector, by 2 vectors. The component ij of matrix M is the component I of this vector times the component j of the second vector. And it is divided by sigma, that is the entropy protection rate. So if you put this and this sigma inside into this equation, you get R. So the condition that should satisfy the friction matrix is that it should be positive semi-definite. R is positive semi-definite, so the only condition is over sigma, the entropy protection rate. That should be positive.
Sorry.
Yes.
Is this systematic and unique? Can you show that really the reversible part is 0 and that there is no other n?
This is not no. I didn't prove that. I can only prove that this is a solution.
This is one possibility.
Is one possibility. I don't know if there is another one. You propose this form, and we still don't have what is the. I didn't know the expression for the entropy. This could be useful to see what are the conditions of the entropy also. But at this stage, I just try to write this in the more general possible.
But for demonstrating that the evolution is irreversible, can you show that L is equal to 0?
If the evolution is that L is equal to 0 is because you don't have a part of the evolution that you can represent with the mechanistic way, proportional to some gradients of the energy. This will be the case if you have, for example, instead of, I'm not considering here the spatial dependence of the density. No, this is a homogeneous system. But if you have spatial dependence and perhaps a flux that is constant, this is something that is not dissipative. If you neglect, if it is perfect fluid and you neglect the viscosity, and in that case you will have an L different from 0. But in this case, we will only have decay to equilibrium that is governed only by the thermodynamic forces that are the derivative of the entropy. Okay. So to have M positive semi-infinite, you have to have the entropy production positive, and using this expression for the entropy that can be derived from the definition of Boltzmann definition of entropy, and also using it can be demonstrated that this is an appropriate expression for the entropy using the Boltzmann definition. And using the definition, the expression for sigma after some calculation, it is possible to show. I will not go into the details, but I just tell you that it is possible to show that sigma is always positive for this expression of the entropy. So the combination of this equation for the entropy and the previous equation for the friction matrix is the underlying structure for a reaction system with the detailed balance. So it is demonstrated that this entropy always increases until all concentrations reach the equilibrium values.
Didn't you just show before that only the reversible term will always lead to a derivative of S with respect to t positive? So before you showed that ds of dt is always positive. So
yes.
then we find assumptions.
Sorry, the matrix had to be positive, definitely.
Yes.
But you didn't a definition for the entropy.
No. I didn't give a definition for this, but from the beginning you
you show that, okay? All you need is that L is an antisymmetric matrix.
Yes, yes.
It's an antisymmetric.
Yes.
That's all you need.
And it's symmetric.
Symmetric. That's all you need.
Yes.
And why do you need more assumptions to prove?
Well, I need more assumptions on the entropy production rate, because M, to be positive semi-definite, M depends on the entropy production. I arrived to an M that depends on the entropy production. So M to be positive semi-definite, then the entropy production should be positive. So to calculate the entropy production, I assume the Boltzmann definition of entropy.
Go ahead.
Now the other example, first diffusion. Now I have only one species of particles, but with spatial and temporal dependency. And we consider this equation in which we only have a diffusion process, but not drift. Later I will add a drift process, drift vector here. So This is actually the Fokker-Planck equation, but without drift. B is the diffusion matrix, and this equation without drift leads to an equilibrium solution that is homogeneous. Again, we have only irreversible evolution in this case to the homogeneous stationary solution, so the Poisson matrix is equal to 0, and we have to write the derivative with respect to time of the concentration in terms of the friction matrix and the derivatives of the entropy. Now this is a functional derivative, and this is a big dot represents also integration in the prime in x prime. So I am derivating with respect to n of x prime, and I have to integrate in x prime, so this is only a function of x. And this functional derivative can be represented with the partial derivative when small s is the entropy density given by this. Well, I put the solution directly, and after some calculations, it is possible to show that the friction matrix is this. That depends on the second derivative of the entropy that appears here, and it is also possible to show that the friction matrix is positive semi-definite only if this second derivative is negative. I mean, the entropy is convex. Well, again, using the Boltzmann definition, this condition is satisfied, and also this M and this form of the entropy composes a generic structure for a diffusion system. But perhaps more interesting is this more general situation, the Fokker-Planck equation, in which we have the Fokker-Planck equation is minus the divergence of the current, and the current has these two parts, the drift and the diffusion part, with the B is the diffusion matrix and A is the drift vector. This is now, because of this drift in the system, this is no more isolated. Think, for example, in a system composed with water and ink diffusing in water, where the Fokker-Planck equation gives you the evolution of the ink inside this reservoir of water. But it is not isolated, it can interchange energy with the water. And the question is, what are the appropriate variables to describe the combination of system and reservoir? In the book of Oettinger says that a crucial part of generic modeling is the choice of the state variables x, or in other words, the definition of a suitable system to describe certain phenomena of interest. So this is actually the difficult part of the theory, because you don't have a clear method to incorporate new variables to describe the system, and the method is actually trial and error. With only n for describing the system, it is not enough to describe the system and the surrounding. You cannot arrive to a generic structure with only n. You cannot arrive when you try to put the Fokker-Planck equation in terms of the matrices L and M, you don't arrive to an antisymmetric matrix for L, for example. L is not antisymmetric. The criterion will be that the set of variables is validated by the possibility to produce a generic structure. So I will try using some reasonable assumption to incorporate new variables, and they will be validated by the possibility to produce a generic structure. The first idea is the following. Since using as I told you before, the Boltzmann definition of entropy, you can arrive to an entropy that depends on the concentration N and also on the equilibrium concentration NE. This NE has information about the surrounding, because the interaction between the system and surroundings makes N, the concentration, evolve to the equilibrium concentration, NE. So this equilibrium concentration has information of the surrounding. So I propose to, in equilibrium, again, when you propose, assume the tight balance of the current equal to 0, then there is a general solution for the Fokker-Planck equation, that is this one, an explanation of this potential field that depends in some way on the diffusion matrix and on the drift vector. This is a general solution for the equilibrium state. So as an additional variables, I propose this NE, where with this equation, simply the derivative with respect to time is equal to 0. But again, this is not enough. When you try to write the generic framework and derive the matrices, L is not antisymmetric. And you need to add another one. The one that I added is the energy density, the total energy density. The energy density of the system can vary, but the energy of the system can change because of the interaction with the reservoir, but the total energy does not change, so that the time derivative of the total energy is equal to 0. And the derivative of the density of the energy could be equal to 0, it could be always constant, or it could be proportional to some the diversion of an energy character. I will show you only the most simple case in which the energy density is always constant. This means that when you start from an energy density constant and when the system loses energy, the reservoir incorporates this energy in the same point in such a way that it keeping it homogeneous. It's not distributed. It could be other cases with currents of energy in all the combination of system and reservoir, but if you consider the other situation, the possibility they produce the same conditions of the entropy density. This is what I'm looking for. The conditions of the framework, and I mean these lesionarity conditions, and also the conditions of the symmetric and symmetric, the L and M matrices, can give you conditions on the entropy. If you don't know the specific shape of the entropy function, can give you conditions on the entropy density. And these conditions are the same independently of this possible situation for the total energy density. Well, and another assumption will be that the entropy density depends only on this is something I said before, only on the concentration and the equilibrium concentration. This is something that comes from also is seen from the Boltzmann definition of entropy. So, well, with this assumption, this is the set of variables that we have, the concentration, and we added this to the energy density and the concentration in equilibrium. These are the derivatives of the entropy, these are the derivatives of the energy. The entropy depends on N and on E, and the entropy only on the entropy concentration. And now we can find the L and N matrices, and in this case you have a generic structure. But before that, we have to separate the reversible and the irreversible parts of the current. This was done by Van Kampen in the 50s. There is a reversible drift and irreversible drift, where the reversible drift, this V, is given by this function. I mean, it is not simple. The drift vector and the matrix, the diffusion matrix, is the separation with reversible and irreversible. The diffusion matrix, the derivative of the diffusion matrix times the equilibrium solution is in the reversible drift. So with this separation, we have this set of equations, and we can write the friction matrix in this way, and the Poisson matrix that is now antisymmetric. Just doesn't matter the details, just to show you the more or less the shape that they have. So the condition that they to be positive semi-definite, and also the degeneracy condition gives you some condition on the entropy, as I told you before, on the entropy density, that close to equilibrium mean that the entropy should have this shape, that simply a maximum close to equilibrium. This is an inverted parabola, and this shape close to equilibrium is also satisfied by the Boltzmann definition of entropy for a dilute solution, and enters in the previous class of functions. With this entropy density, we can also get an entropy balance equation, and we can analyze the entropy production term here. That turns out to be this. This is the diffusion matrix multiplied by the same vector from the left and from the right, in such a way that since this diffusion matrix also has to be positive semi-definite, the entropy production is always positive semi-definite. Well, there are too many questions. Perhaps let's see some examples. From examples of this is the most simple diffusion process that we can think about. Just in
Before going into examples,
yes.
the Fokker-Planck equation,
Yes.
where stationary distribution is the exponential of what you call entropy.
No. The stationary, the equilibrium solution is the exponential of the potential, that is the function attention. This is the equilibrium solution, this is the exponential, and the general solution is this one for the potential. Then, this is on the book of God and book of stochastic methods, for example.
And this is what you would call free energy?
No.
Because that was one of your statements at the beginning, that you had energy, that you had entropy, but yet you had to put that into the context of the free energy.
Well, that's for equilibrium thermodynamics. No, I was talking about equilibrium thermodynamics.
But if those are isolated systems,
Yes.
the stationary distribution is the equilibrium one.
Yes.
Then this potential should be the free energy.
Yes. And you can identify this potential with the free energy.
Well, but I don't understand neither the question nor the answer. Well, until you say what is A and what is B, talking about free energy, this can be an equation for the social dynamics of something on Twitter. I mean, it's not still you don't have. You started with a generic Fokker-Planck equation.
Yes.
So this is not thermodynamics. You are trying to write this into something which has some reversible part, irreversible part. So in a generic framework which resembles thermodynamics. But you are not using free energies or anything like this. So.
But I think that he's saying is understanding or interpreting what he writes in terms of thermodynamics. And what he said is that he would put that into the framework of a free energy.
Yes.
Well,
now,
it will be equilibrium anyway. It will be only for equilibrium.
But those systems are isolated, so the stationary distribution is equilibrium.
But I don't use
So the definition of the free energy is only for equilibrium.
Yeah.
So
But the stationary distribution is the equilibrium.
Yeah, but outside the equilibrium you don't have the free energy.
Yes, you can. Perhaps it's a question of.
You can only define it on equilibrium.
Yes. Then?
what is it?
Is this the free energy?
This is the free energy for equilibrium.
If you can, perhaps it's a question of night. So perhaps you can call this a free energy, but you don't use in the framework the free energy to describe the evolution of the system, only for the equilibrium solution. For the evolution of the system, we use the entropy that appears in this generic framework. The entropy and the energy, the total energy. Well, and this is, as I was telling you, this is the most simple diffusion process in one dimension. You start with the Gaussian, and the Gaussian is always step is fatter, lower. But now we can also calculate the entropy production rate, and you can see that the entropy for different times, for the same times that appear here, that the entropy production rate is larger in the region where you have a maximum current, no? Because in the size of this Gaussian are the regions where you will have current to the left and here and to the right here, and in this region are where the regions where you have entropy production. This is perhaps the more interesting example, the Cramer's equation for Brownian motion, because well, this is an equation for the Brownian motion. The equation is for this density F that is defined in the space of momentum and position, and in this case only in one dimension, P and X, momentum and position. So you can have a given distribution of momentum as an initial condition that could be very different from Maxwellian distribution, equilibrium distribution of moments for given temperature. The temperature that appears here is the temperature of the reservoir, but not necessarily the temperature of the Brownian particles that we are describing with this equation, because these Brownian particles can have any distribution in momentum. You can start from any distribution momentum or completely out of equilibrium. This is then we are outside of the local thermal equilibrium hypothesis. So in this simple example, we can be outside of the local thermal equilibrium that is used in classical irreversible thermodynamics. The stationary solution is this one, and you can have this potential here that could produce exchange of energy between the Brownian particle and the surroundings. You can calculate also the entropy production that has this shape for the. It is easy to see that for the stationary solution, if you replace here the stationary solution, the entropy production rate is equal to 0 in equilibrium, and is always positive outside of equilibrium. If we plot for example, the density of particles against position for a potential that has the shape of the double wall, and you start for an initial condition that the initial condition is this one, the homogeneous solution. So for the system, this homogeneous concentration corresponds to the maximum entropy only for the system. And as time goes on, you end up with this concentration with maximums in the walls of this double potential. This solution at the end has a more structure than the initial condition, so the entropy should decrease. Of course, the combination of entropy of the system and the entropy of the reservoir should always increase. So now we can calculate the entropy only of the system, or the system composed of this Brownian particle, and the total entropy, the combination of the entropy of the Brownian particles and the surroundings, that is always increasing. One decreases because you end up with a more structure, but the total always increases. Well, in conclusion, the generic frameworks were proposed for reactions with the tile balance, reactions in an isolated system, and also for the Fokker-Planck equation. We can combine, of course, the results of these two equations to describe a reaction diffusion system, but always, of course, with reactions with the tile balance. For a non-isolated system, like the one represented by the Fokker-Planck equation with the drift, the reservoir can be taken into account by including additional variables, especially the equilibrium solution, among the system variables. And also the requirements of the framework can be used as a guide to obtain the entropy balance equation, and also the entropy production. Well, thank you very much.
Thank you, Miguel. More questions or comments? Wait.
So it's not clear to me. The data balance is not valid from the preview. I think usually the data balance in general is not valid from the preview.
Out of equilibrium, no, of course, only in equilibrium. I'm assuming that these equilibrium solutions are the solutions for which the data balance holds. Because there are stationary solutions in which, for example, the Fokker-Planck equation have solutions in which the current is different from zero. These are stationary solutions, but data balance is not satisfied. But I consider only the equilibrium solution in which data balance is satisfied. Of course, outside equilibrium never is.
Sorry.
Students, do you have any questions?
We are forgetting our Chairman. Chairman is here. More questions or comments?
I know the kind of non-isolated systems you can build. You have shown the example of the Fokker equation where you have this temperature. Which can, so only thermal systems in thermal contact, can you also include any chemical contact, or what? Which kind of non-isolation can you take?
I have only an intuition about this. I think that you can represent only system with only one reservoir, because when you put more than one, you can have flux between the reservoirs, and you never reach equilibrium. But you have only one reservoir, for example, reservoir of particles, also different particles. You reach always an equilibrium of the total system. But if you have more than one reservoir, if you fix the concentration of two particles, you can always have a reaction power that is always different from zero.
Can you have several reservoirs, but of different types? For example, source of charge and mass. And you can have
Perhaps, I don't know.
In which sense is this related or not related to the general theory of looking for non-equilibrium potentials?
Looking for non-equilibrium potentials.
What your colleague Gonzalo Horacio has been doing for 15 years.
Functionals.
Yeah.
There is some relation, yes, because the entropy in some cases is the same as the electrical function. And but I didn't see specific examples, but there could be, yes, some examples in which the descriptions in terms of the electrical function can be transported to this framework. But there is perhaps a difference. I don't know. The framework imposes you usually use the condition of the second law of thermodynamics. It tells you that the entropy always increases. But the condition that this matrix be positive semi-definite is actually a stronger requirement, because it means that this product is always positive for any vector. But you require the second law requires this only for these vectors. So this is a stronger requirement, and perhaps this is a difference in this theory.
Okay. More questions or comments? If not, I remind you that Monday at 12 you can learn about the life of some physicists. Thank you.